This is presentation for machine learning prediction model. My name is Daniela Stefanova. The task is to build a model to predict the electrical energy output of a combined cycle power plant which uses a combination of gas turbines, steam turbines and heat recovery steam generators to generate power. We have a set of 9,568 hourly average ambient environmental readings from sensors at the power plant which we will use in our model. The features represented in columns in the dataset consist of hourly average ambient variables: temperature, ambient pressure, relative humidity, exhaust vacuum. We are trying to predict the net hourly electrical energy output PE. We want to make predictions by learning of the input-output relationships. Our goal is to create a model that makes accurate prediction on new unseen data, predictive modeling. We cannot estimate performance on data we do not have, so instead we will split our dataset into two sets. Training set, to build and train the model, 80% of the dataset, 7,655 readings of the given dataset. And test set to evaluate model performance, 20% of the dataset, 1,913 readings of the given dataset. Considering the fact that we have relatively simple, fixed, predetermined set of past observation of features and targets, I will use supervised parametric algorithms. I will use Excel for analysis. And first of all, I will perform simple linear regression for all features separately in order to see dependency of PE from each variable. And then I will proceed with multiple linear regression because we have 4 variables. Simple linear regression shows us the influence of the single independent variables on the output dependent variable PE. I have scatter charts with a trend line for all variables. In the first diagram, we can see that with increasing of the temperature, the electrical energy output PE is decreasing. The slope line is negative. In the second diagram, with increasing the exhaust vacuum, the electrical energy output PE is decreasing. The slope line is also negative. In the third diagram, with increasing of the ambient pressure, the electrical energy output PE is increasing. The slope line is positive. In the fourth diagram, with increasing of the relative humidity, electrical energy output PE looks like that is slightly increasing, and the slope line is also slightly positive. In the next slide, I am performing multiple linear regression where all features are included. This is model 1. Interpretation. Multiple R, correlation between predicted PE in measured PE, in this case is 0.96. R square, tell us that how well the regression line approximates the actual data. 93% of the variance in PE can be attributed to our variables. Standard error measures the average deviation of the errors of the regression model. The smaller the value of the standard error of the estimate, the better the fit of the regression model to the data. In this model, standard error is 4.53. Significance indicates the probability that all the coefficients in our regression output are actually 0. In this model, it is 0, and that means that the model is good. P-value. Low p-values indicate that variables are statistically significant. Value less than 0.05 is considered significant. In this model, all variables are close to 0 or equal to 0. The largest p-value has ambient pressure. Coefficients. Bias or intercept, 454.94. Weights or coefficients. For temperature, minus 1.99. For exhaust vacuum, minus 0.23. For ambient pressure, 0.06. For relative humidity, minus 0.16. The multiple linear regression equation is given at the bottom of the slide. In the second model, I am excluding ambient pressure because it has the largest p-value. Multiple R in this case is 0.96, R square is 93%, Standard error of the model is 4.54. Significance in this model is 0. P-value in this model, all the variables are close to 0 or equal to 0. The largest value has vacuum variable. The equation of the multiple regression is at the bottom of the slide. In the third model, I am excluding vacuum variable. Interpretation. Multiple R is 0.96. R square 92%. Standard error in this model is 4.76. Significance in this model is 0. P-value in this model, all variables are equal to 0. The equation of the multiple regression is given at the bottom of the slide. This is a slide about finding the best regression model. Generally, we can choose the model that have higher adjusted and predicted R-squared values. We can also compare root mean squared error of the models, which is the square root of the mean squared error. In my Excel analysis, it is the standard error of the regression. As we can see, the smallest standard error is for model 1. For this model, the root mean squared error is 4.53. The last slide is for evaluation of the chosen model with using the test dataset, and that is model 1. By using the output formula, I have calculated the values for PE predicted and then calculated the root mean squared error. For my dataset, the root mean squared error is 5.04. It is the higher than for the training set, so the model could be further optimized.